Welcome to my creative and physical computing design and evaluation video. I created Wave for this mini project. They're a fictitious digital media agency who focus on allowing younger audiences to visualize sound. After conducting second-hand research on existing contemporary designers, I decided to make an interactive solution which modulates or adjusts objects based in a scene, often audio context and beat signature. Essentially, the main idea for this task is to change the parameters of a shape by extruding it from the lows and the trebles of a song and deforming it based off the vocals and the highs. Based off my preliminary sketch here, you can see I initially figured I could use a sine wave to manipulate this surface by assigning a value which represents the bass, trebles and vocals between a value of -1 and +1, with 0 being the smooth texture of the shape. The object would modulate to the music looking like it was dancing along. Instead, I created an audio context from an audio source, which the user uploads themselves. Once the source was defined, the audio is processed and moved along the chain using audio nodes. An analyzer node is assigned or connected to the audio source, which obtains data based off the audio's frequencies. This is unfiltered, as I do not want to modify the beat signature of the song. I want it to sound the same as the original file. Finally, the audio is delivered to the destination in my script. This can be seen here. FFT stands for Fast Fourier Transform and is a function which allows you to see what kinds of signals are present in your system, in my case an audio file. It breaks down a complicated signal into separate sine waves. The signal is now composed of separate simple sine waves. The default FFT size is 2048. But I opted for an FFT size of 512 as it requires less computational processes, making it easier to perform on consumer-grade hardware. For this, my buffer size is also set to 256, half of this value, meaning a total of 256 data points are collected every time the audio is analysed. Here I then separated this data array into two halves to be applied to the top and bottom section of my sphere in the centre of the scene. Basically, the lower half visualizes the treble and the bass, while the upper half deals with the higher frequencies, for example, vocals. In this project, I have utilized an algorithm for noise, known as simplex noise. The justification for this is like reducing my FFT and buffer size, purely because it's easier to compute. My basic understanding of this is that simplex noise has no directional artifacts, it's totally random, and my thinking was it should not target any specific areas of the scene because of this, and it ended up working as theorized. I found documentation which stated that it was more suitable for a 3D space as it scales to higher dimensions. Further, this algorithm requires fewer calculations, which is paramount for me as I'm not well versed in maths. The bulk of my file is composed of a scene which houses all of the objects and everything I'm producing, 2 lights, a natural and soft light, a spotlight in the center of the scene as well, as I felt this looked best, 3 total objects, 2 planar meshes and a ball or sphere, and finally the render loop to display all of this, which you can see in front of you now. This render loop updates frequently based on the buffer size to render the new transformations upon the objects. I intended to provide the user with an interface that allows you to make the ball more cubic and vice versa. However, after multiple attempts of this operation, I failed to do so. With more time, I feel as this could be achieved with consultation of proper documents and online articles. Upon loading the HTML file, this is what the user will be presented with. This button then has a Tone.js audio cue to know that it's functional. You can then select an MP3, MP4 or WAV file to play your own music. Thank you for taking a step-by-step with me in this process. I hope you enjoyed it as much as I did. Thank you.